Okay. Hey everyone, let's start. I don't have any more announcements today. I think I had too many last time, so yeah. Today we will be talking about filters. You may remember we talked a little bit about filters a while ago, but I wanted to say more about them, so that's what's going to happen. To recap from last time, filters are these ubiquitous data structures. They appear in all kinds of applications: computational biology, databases, networking, storage systems, streaming applications, and many others. And to recap what they are, a filter is an approximate membership query data structure or approximate dictionary. And the most classical type of filter is called Bloom filter. And suppose that this is your set, this is your universe of elements, A, B, C, D, and your set contains A and C, then an exact dictionary, like a tree or a list or anything like that, if you query for A and C, they would tell you definitely yes. And if you query for B and D, they would definitely tell you no. But because filters are approximate, they have one-sided error. They may give you false positives to the data. So here, like, if you ask for A or C, you'll definitely get the right answer. You will see yes. And if you ask for B, in this case, you get the right answer. There's no. But if you ask for D, you get the wrong answer, which is yes. And so a filter has these approximate membership queries where you may get false positives, but never false negatives. So like I said, if you query for some element that is in your set, you get the answer yes with probability 1. So that's called true positive. And if you query for something that is not in your set, you return no with some probability at least 1 minus epsilon, where epsilon is some error parameter, and you get yes, which is wrong, with probability up to epsilon. And epsilon is like a user-defined parameter, and people usually prove bounds in terms of epsilon. Yeah, is this like, do people remember this kind of a bit? Great. Yeah, so the reason that we're interested in filters is that because they allow this one-sided error, you can they can be much smaller than exact dictionaries. So the true dictionary, like a tree, has to be at least n log u, where u is like the size of your universe. So log u is the number of bits that you need to store it. And filter can be is lower bounded by n log 1 over epsilon. And if epsilon is something like a constant, this is much smaller than the exact dictionary. And for most practical purposes, epsilon is like 2%. So if you plug it into this thing, that would be 8 bits per item, like log of 1 over 0.02. Yes. Oh, okay, yeah, log of 0.1 over 0.02 would be like at least 8, I guess. So yeah, so the point is that the filter is way smaller than the exact dictionary. And they're not independent in that, like, usually you don't use the filter alone. You usually stick the filter on top of the dictionary. And so that can prevent you can save some queries to the bigger thing. And last time we talked about Bloom filters, which are the most classical kind of filter, and they're made up of, they're really simple. They're this bit array, and you have k hash functions, where k is something that can be you can mathematically derive what optimal k is, given the number of elements that you have. But the way it works is that in this case, k equals 2. And for every element that you insert into your set, you have to take, because k is 2, you take k hashes, and those give you locations in your bit vector, and you set those locations when you insert something into the set. So here, you hash A, and you set these 2 bits. Here you hash C, and you get those 2 bits. And the bits can overlap. So like here, A and C overlapped there. And so, yeah. So the reason that Bloom filters sometimes you get false positives is because the hash functions may overlap, even though some element was not already set. Like, for example, if you ask for B and B happened to have like these 2 hashes, then you would get yes, even though the answer was truly no. And yes. So yeah, that's Bloom filters. And Bloom filters are good. They've been around since the 70s. But Bloom filters have several issues. The first one is that their performance is higher than the lower bounds. So the lower bound for space for filters is n times log over 1 log of 1 over epsilon plus omega n, and blue filters are approximately 1.44 times n log of 1 over epsilon. So this is like a constant factor more than the lower bound tells us that we can get. The CPU cost is omega, the cost of querying is 1 omega 1 over epsilon, because you can prove that the optimal k is some function of like 1 over epsilon. And so similarly, the locality is bad because you have to check 1 over epsilon slots, and they may not be contiguous. So you have to do at least this many, but ideally we would want order 1 checks and probes, like order 1 checks and also order 1 cache misses. So, yes. So that's one issue with bloom filters, is the theoretical cost. And another issue is that they have a lot of drawbacks in terms of the functionality. So first drawback is that you can't delete, because like you just have the set bit. So if you delete a bit, somebody else may have set it. So it's not right to just unset it. You can work around it. Like if you want to delete, you can just rebuild the entire thing, which is not great. Or you can like maybe buffer your deletes and then rebuild them at some point, which is also complicated. Another limitation is that you cannot resize them. So like you have to fix your bloom filter size up front, like the number of bits. And because the hash function is defined in the space of the bits that you have. So you can't just like, if you want to grow, you can't just like copy the hash function, or you can't just copy the bits you have into some bigger array. But you can, how it works in reality is people usually guess the size and they rebuild the entire thing if you are too big, or if you have too many elements. Another one is there's no filter merging or enumeration, which is something that you might want to. Merging is like you have 2 filters and you want the output of both filters into one destination filter.
If you want to review the whole bloom filter, you have to have all those inserted values.
Yes, that's why you need like usually you need a dictionary underneath the filter as well, because you cannot regenerate exactly. You cannot regenerate like a bigger bloom filter from a smaller bloom filter because you don't have the initial elements.
And for something like stream data, we cannot have all those parts values. So
Yes.
rebuild is not.
Yes, exactly. So this rebuild assumes that you can have the static data. I don't know what you do if you have stream data for bloom filters.
Yeah, today I have another class with
Oh, did they also do this?
network class, and yeah, they introduced bloom filter application on networks.
Okay.
And they will have stream data. And they just use bloom filter as a set to look for if an element exists or not.
Mhm.
They don't want the exact.
Yes, but what if, yeah, like you could, but if you run out of space in your bloom filter, but you don't have the initial elements, did they mention how you can rebuild it? Or they just say that you know n upfront?
They said they can reset the bloom filter, and I don't know.
You can reset the bloom filter.
I think they just discard all of those.
Oh, they just like, maybe you just start again?
Yeah.
Yes, okay. Yes,
What would be the problem with streams? You can just keep inserting.
you keep inserting, but you have to guess the size up front. Because you need to allocate like some number of bits up front in your bloom filter.
But like if you have like a very large plant, just keep going, because like even if you don't know the size on a computer, you have only fixed space. So
I see, so you're saying like you could provision it for like the maximum memory size you have? You can, it may not be very space efficient to do so.
no, but like you wouldn't be using, like as in like you do provision, but like it's like you don't actually have to use it. Like you only start to use it if you need it.
But like, so the hash function, you like hash and then you mod like the size, probably. Or like those, you can compute the hash mod like the number of bits you have, which tells you your slot.
Right, like so the mod value, okay, yeah, I was thinking like you could build it like a vector, you can just keep increasing how much you want out of what you provision by like.
Yeah, like you could do table doubling. But like, there's no way to get back the values into the new table. Because like something mod n is not the same as something mod 2n.
Right.
Yeah, so in this sense, like, if you have the data, you can just rebuild, and it's true, like, maybe you could say, like, you can make some amortization argument about how, well, you already added n things, so if you just add two n things, it's like order one. It's okay, I guess, like, the latency is not amazing, but it does require you to have the underlying data, which is not necessarily always true, like if your stream is just passing by. Yeah, so there are workarounds, like they can work in some cases, but not all. Another main limitation is that you don't have merging or enumeration. Merging is like you have two and you want to have a third Bloom filter with, or a third filter with everything that was in the two source filters. But there's no like correct way to do that with a Bloom filter, because the hash functions may have been different in two, or the hash functions, they may not be different, they may be different size also. And also you cannot get back the elements in the, or like, yeah, you cannot get back either the hashes or the elements or anything. And you do want merging, because like, if you remember LSM trees, you stick the filter on every subtree, and you have to merge the subtrees, and ideally you would like to also merge the filters. And there's, I don't think anybody knows how to fix this in Bloom filters.
Also review, create a new one.
You can rebuild, but you also need the base data.
Uh,
If you have the base data for two, you can, yeah, you can make a new Bloom filter. That's true. I don't know if that counts as merging, like, because then you're just like starting a new filter, so. Yeah. And then last one is in the initial Bloom filter, there's no values with the keys, and sometimes you may want to also get the values back and to associate it with it. Oh, and another reason that you may want values is if you want counts, like, you may be interested in counting the frequency, but there's no way to natively do this in the Bloom filter, so usually people combine it with another data structure. Yes.
Am I missing something, but like in a tree, merging makes sense, but like for a Bloom filter, merging is just resizing.
Sorry?
Like in a tree, merge, it's like a different operation, but like for a Bloom filter, isn't it just merging like resizing?
How is it just resizing?
Because like you are adding it, like merging is like you take two Bloom filters and make another one. Or like you can like somehow combine it, but it's the same as resizing.
It's not correct. Like if you have two Bloom filters, like you can't just like concatenate them to make a Bloom filter that represents.
So the merge, like, I'm just confused as how you define the merge operation.
The merge operation is you have two filters and you want a third filter that contains all the elements of the first two filters. Like that, you want a third filter that would result if you had added all the elements that you added into the first two filters. And you want it to be correct.
So how does that like resizing correspond big enough so that
How can you resize the first one to contain everything from the second?
Have the size of the second.
Yeah.
And then you just add everything.
If you have the base data, yes. But you want to do it, you don't want to iterate over the dictionary, ideally. Like if you can iterate over the dictionary, it's true, like you can add everything from the second set into the first one, and assuming that you had enough space in the first one. I mean, this also gets into the issue of no resizing, like, if you were able to resize, and if you did have the base data for the second one, then you could re-add everything from the second one into the first one. That's true. But you may not know the sizes up front as well. Yeah. So I guess the point is like, you can maybe work around these things, but it's like, we're kind of, like, it may require some difficulty. So these limitations, at least they make it more complicated because we have to like come up with these different schemes, and they may sometimes work or may sometimes not work. And also they may waste space, like table doubling is not always, table doubling is like an extra factor of 2 at most. And also they can slow down the performance. Like if you have to rebuild the entire thing, you may introduce like a large job in the middle of your application. So first I want to talk about a different kind of filter called quotient filter. And quotient filter it's due to this old idea from Canute from 97. And basically the idea is kind of like caching in a sense. So the way it works is that you still use hashes, but for every element, you take some fingerprint hash. So you have some element X, which takes log of U bits, and you want to hash it down to something that takes P bits. And you get, so instead of doing like 2 bits or K bits in the Bloom filter, every element now has this fingerprint. And the only way that you can get false positives is that 2 elements got you the same fingerprint, like hash of X equals to hash of Y. And then you get the false positive if one of them was stored, but the other one wasn't. And the probability that you get these 2 that collide is 1/2 to the P, where P is the size of the fingerprint, because that's the probability that they line up. And basically what is going to happen is that we're going to use these fingerprints to index into an array in the same way that we did caching.
So what is the difference between a fingerprint and the hash that like a Bloom filter would give you?
The hash that the Bloom filter gives you is used as a location. I guess here it's also used as a location. In the Bloom filter, there's K of them, and here there's only 1. And you use the entire fingerprint, or sorry, you use the entire hash of the Bloom filter. In the Bloom filter, you use the entire hash as the location, and you compute several of them. Here you use, I'll show you the exact details, but you use like the upper bits as the location, and the lower bits you explicitly store them.
I see.
Yeah, so that's why I say it's like caching, because like in caches, like if you remember from a while ago, like the upper bits tell you which set you're in, and the lower bits, you actually, like the entire thing is the address. The upper bits tell you the location in the cache, and the lower bits are like, then you store that address. So does that make sense? I'll explain more, and then you can tell me if it doesn't make sense. Okay, so yeah, so exactly like I said, you have this fingerprint, which is P bits, and then you divide it up into 2 parts. The upper one, which is the bucket index, and the lower one, which is the tag. This is Q bits, this is R bits, and Q plus R is P. And the upper Q bits tells you the bucket, like the index in the array that it goes into, and the lower R bits tell you what is the tag, and you explicitly write those into the array. And this also has different from Bloom filter, because in Bloom filter you never explicitly write any of the hash. Yeah. And this is basically like, you can think of it as like a direct math cache in some sense. Like the upper bits tell you the bucket, and the lower bits are the actual tag. And yeah, so this is, oh yeah, and the size of the table is 2 to the Q, where Q is the number of buckets you have. And yeah, so suppose you have X, which is your first element, and suppose that we got a new element Y, which hashes to the same bucket. So this is like the main challenge for these filters. Anything like this that uses hashing is like about collisions. And ways that we could possibly resolve collisions includes linear probing, which is a traditional way in hash tables of addressing the collisions, like you keep walking forward until you find some free slot. Or you can do Robin Hood hashing, which is a more fancier way of resolving collisions. And Robin Hood hashing basically tries to equalize the distance. Everybody has like a true bucket that they want to be in, that depends on their upper bits. And Robin Hood hashing tries to like equalize how far everyone is from their true location, in a sense. Yeah, so it's like it requires some more computation than linear probing, but you can reduce like the worst case time that you have to access anything. Okay. And yeah, so in either one, I think in linear probing or in Robin Hood hashing, in this example, we would put T of Y, even though they both are supposed to go to bucket 4, we put Y into bucket 5 because there's no space in bucket 4. And somehow we need a way to tell if T of Y truly belonged to bucket 5, or if it truly belonged to bucket 5, or if it was like displaced from bucket 4. And we can use order 1 metadata bits to tell us whether or not that's true. Okay, so how do you resolve these collisions? There are 2 metadata bits per slot. Just like these are your slots. This is R bits each, and then this is 1 bit each. And there's 2. One is occupied and one is run in. And occupied tells you whether this bucket is actually occupied, like occupied tells you whether this bucket is occupied by something that like truly belongs there. And run end means that it is the end of something that like started earlier. So here, in this example, T of A truly belonged in this bucket, and P of D and E both also belong in this bucket, but they had to be displaced. And run end tells you that this is the end of the things that belong here. And same for here, but also, now occupied is here, and M was supposed to go in here. But because it's not data bit is set, then you know that the start of this run is actually here, because the end of the previous run was there, and the end of this run is here. The metadata bit is set. Yeah, and I guess this is just this is how you would represent it with like chaining. Okay, so suppose that we wanted to add a new element. Yes, we're adding B. Yeah, okay. So suppose that we wanted to add H of B. I guess these are stored in sorted order. Now B belongs in this run, and occupied bits stay the same, but the run end bits shift over by 1.
Where do you have the, like, why is it spiking?
I guess
Why-
here they're stored in order. Like I guess the fingerprints are stored in order. Or sorry, the lower bits, like the tag. So this is assuming that the tags are in order of the elements. Which is not necessarily true, but it is in this example.
But by doing this, wouldn't it just become like more expensive? Like for one, just the search itself is really expensive. It's almost the same as chaining.
This is cheaper than chaining because chaining you have to store the pointers. This is like linear probing.
Yeah, but like, let's say you want to search for D, you still have to you go to the run ends, and then you have to search the whole run ends, which is essentially the same as doing chaining, where you have to search the whole linked list or whatever implementation you have.
Yes, but they are contiguous in the array. So it is faster to leave the contiguous memory.
Keeping the order here cannot speed up the search, because we still cannot use something like binary search. But we need to know the raw ends. We need that in here.
Yeah, you have to find, I guess you have to find the run ends, but because these are 1 bit, you can probably find it fast. Because these are bit vectors, so you can just you could like find the next set bit using bit tricks, or something. And you could probably do that faster than well, first of all, you cannot do that with a linked list, like you cannot find the end in binary search on it. Here you actually can, as long as you find the run in. I'm not sure that they do, because in practice, I think these runs are usually not very long, so it might just be fine to read forward. But I think you actually can find you probably can find the end pretty fast using find next bit. Does that make sense? Okay. So that is quotient filters. That's it, pretty much. And quotienting, it allows a lot of features that didn't happen in the Bloom filter. First one is good cache locality, because you have to just write one element into the quotient filter, and maybe you have to do some shifting, but all the shifting is contiguous. Whereas in the Bloom filter, you had to do like arbitrary probing based on your hashes. It scales out of RAM efficiently. It can support deletions. As long as, if you do counting, it can support deletions. You can enumerate the fingerprints. You cannot enumerate the initial elements, but you can enumerate the fingerprints, because like you just need to concatenate the top and the bottom bits. You can merge them, because now the hashing doesn't depend on, the hashing depends on the size, but if the sizes were the same, you can merge. And you can resize, like you can just put this in the first half. And yeah, you can maintain counts. You can associate the values just with the fingerprint, and you can use variable size encoding for the counts. And there's a variant of this called counting quotient filter that allows you to support the counts.
It's a really quick, this thing I stepped back.
Mhm.
And in the last slide, this was a paper from 2007.
Yes.
But wasn't this proposed in like 97? You said earlier?
Yes, this idea It's like this idea of storing like the high bits and the low bits is from 97, but I think the implementation, there was no fast implementation until 17.
That makes,
And I guess no fast and no like, I would call it like general implementation that supports all of these features that we might like.
I,
Yeah.
thanks.
But yes, the idea is not new in 2017.
You said we can use, we can use this to do resize, but here, wondering the size of our array is still by the, I mean, correct, by our fingerprint.
Mhm.
So if you want to resize it, you have to choose another fingerprint, for example, makes the length of fingerprint larger.
Do we have? Oh, I see. I see what you're saying. You could just move, you can make, so like suppose you made this 2 to the q plus 1. You can make the quotient bigger and the remainder
Oh.
smaller.
So we have a upper bound for resize.
Yes, I guess like you cannot resize, you can resize up to like p minus 1 probably. But you would just like cut the boundary differently. A question.
When did we do one? Why plus?
Like if you doubled this, it would become 2 to the q plus 1.
But
And
for
then-
logic,
For merge? For merge, like if you had 2 that were 2 to the q. If you have 2 filters that are size 2 to the q, are you sure? Depends on if you're trying to merge them into something size 2 to the q or size 2 to the q plus 1, I guess. But either way, as long as both agree about the size of the thing that you're merging into, you can just use the fingerprints as before.
and delete would be more expensive than like a traditional chain with prediction,
Is delete more expensive?
because you have. to-
Yes. Because you have to shift rather than swing the pointer. I think usually, I think in expectations, the chains, the runs are small, but in practice, are they actually slower? Because in chaining, you have to swing the pointer, like you have to access 3 nodes in your like list, at least. Is it like you have to swing prev into next. But here, if you read like 3 cache lines contiguously, you probably don't have to read 3 cache lines contiguously usually. Like it is cheaper to read 3 cache lines than 3 linked list nodes.
Right.
Yeah, then you have to move everyone down. Yeah, it depends. Yeah, it depends on like the size of the chain and who you are removing in the chain.
Yeah, no, then you have to do voltage.
You have to move the whole dictionary.
Or is it just creating space?
Yeah, in this case,
Let's say you delete to your page, then you have to move every TFT to TFT. One, like that,
yes.
because you're occupied.
Is that, would it be fine to just move, like if you deleted A and you move, you definitely have to shift D and E down. You can you can maybe keep T, M, and P there if you keep the metadata bits like they are.
But you.
It would probably be wasteful. You would probably like to move them down also, because like you probably want things to be as close to where they're supposed to be as possible. Yes, it depends on how long the chains get, and it depends on like how many of them are close to each other, for sure. Good question. But also pointers are bigger than, if you are interested in space, like the remainder bits are probably smaller than the size of the actual pointer. This pointer is like 64 bits, and remainder bit is definitely, remainder is like less than 64 because the whole thing is 60, the whole fingerprint can at most be 64 bits. Yeah, so let's keep going. To go back to the theory, the lower bound is this, and log over 1 over epsilon plus omega n. Quotient filter gets closer to it. It's this, which is matches the upper term plus the constant is 2.25. And the cost is, in expectation, it's order 1. And in terms of the locality, you have to probe to the first and then you scan forward. And scanning forward is usually pretty fast. And yeah, so there are these theoretical advantages over blue filter in terms of space and also in terms of CPU cost. But it's an expected thing because hashing is randomized. Yeah, so these are some experimental results. Up is accurate, this is accuracy, up is good, and X is number of bits per element. And we expect that accuracy improves with number of bits per element. And red is quotient filter, diamond, black diamond is blue filter, and triangle is counting filters. So, yeah, there's crossover between blue filter and quotient filter at false positive rate 1/64. And these are the bounds, I guess. You can analytically determine what the crossover is. Yeah. And so you can see like, as the number of bits increases per element, which will happen when the number of elements grows large, that quotient filter gets more accurate per bit. And in terms of performance, this one is insertion time or insertion throughput. Up is good. This one is load factor, and load factor is just like how full is the quotient filter or any filter. And everybody, it's always expected the performance will degrade as the load factor increases. Blue filter, I guess except for blue filter, which is constant, because you just need to set the bits. There's no like collisions, or you don't have to like account for any collisions really. Quotient filter and pending filter both degrade, but there's a crossover, maybe like past 90% load factor. And then this one is frames per second, false lookups per second. Yes. X is load factor, and again, this one is quotient filter, this one is blue filter, the counting filter, and then so yeah. And I guess counting filter, the false lookups are fixed, but quotient filter are not, because like you may have collisions. Okay, so to recap, we talked about these blue filters, there's quotient filters. Another kind of filter is cuckoo filters, which are also popular. These two are probably most popular these days, and there are others mostly based on hashing and mostly static. Quotient filters and cuckoo filters are dynamic, which means that they can accommodate dynamic data, but the other ones usually cannot. So revisiting the plot that we had earlier, when I was talking about load factor, throughput, this is load factor, and the performance degrades as the load factor increases. This is green is quotient filter, blue is cuckoo filter, and purple is another one called Morton filter. And all of them are pretty bad, around like 90 to 95% full. And the problem with this is that a lot of applications are write heavy and they maintain the hash tables at high load factors. So you have a trade-off between space usage and speed in filters. So like for cuckoo filters, so like left in load factor is like less space efficient because you can always provision bigger than you actually need, and you can get this high throughput by trading the load factor, but you have to pay for it in terms of space. And likewise, like you can get more space efficiency if you fill it to high load factors, but you have to pay in terms of throughput. And right now you have to, if you have an application and you want to use a filter, you have to choose between space and speed. But ideally, so we want to investigate what happens here and whether we can do better. Because we don't want, ideally we want to overcome this trade-off between speed and space. Okay, so like we were talking about, the main issue with quotient filters and why they're slow at high load factors is because of the shifting. When there's too many elements, they get close together, and then if you insert something, you have to shift all the other stuff down. And yeah, so yeah, you have to find the run, you have to shift everything down by one slot, and then you have to store the element. And then the shifting increases as you have more inserts. And cuckoo filters, which do you all know what cuckoo filters are? Okay, this is exciting. Cuckoo filters are really cool. basically the way it works is that you have like a 2D array. Thing. And you have this element and you use two hash functions. H sub 0 and H sub x, and that tells you which, you can think of this as like a cache, like you can think of this as like which line in the cache, or which set in the cache am I supposed to insert this into, based on the hash. And the thing is parameterized by n, which is the number of elements, and s, which is the number of slots. This is like the waves in the cache, it's the number of slots per block, and it's usually a constant, so like 4. And the way Cookie filters work is that you compute these two hashes, you insert it, you only pick one to actually insert it into, but you examine them and you pick which one is less full. And then you insert the thing into the thing that's less full. And if both of them are full, then you have to kick an item elsewhere. And the way that you determine where you kick the item is everybody had two hash functions. So, and they got put in one, so now you just check the other one. And then you kick that, and then you may have to keep kicking if you have the same issue down the line. So suppose that this is our Cookie filter, and we have this, we want to insert this element X, and these are the two hashes, and both of this sets are full. And so arbitrarily, we do tie breaking, we pick this one, and we have to kick something down, and suppose that f of 8 got hash, it's two hash functions, or like here and here. And so you have to kick it down there. And now f of 12 is going to get kicked. But f of 12 also had two hash functions. So at the time when f of 12 was inserted, this was less full. But so it got inserted here, but now you check its two hash functions, and it got hashed here and here. And so now it's 12, this pre-slot. Yeah. So then you move 12, and several things may have to shift. Here we inserted X, but we had to kick 8 and we had to kick 12. And the issue is kind of similar to quotient filters. When you get higher load factor, you have to maybe kick more down the line because more stuff is full. Does that make sense? Like how you do this? And there's math to support this. Yes.
Also, looking at the ensure that, like, for example, if you're converting X of X,
Mhm.
then you have to pick F sub A. And then if you add S sub A to the second line and you kick out S sub, but then for adding S sub, you have to kick out S sub X again. So like, how do you ensure that there's no cyclic dependency?
Oh, I see. You're saying like, can you get a cycle? Yes. You can get a cycle. Maybe you resize when you get a cycle.
Right.
Maybe you just resize the entire table.
But then wouldn't that like make the problem even worse because now the number of hash outputs would increase?
If you make the table bigger,
Oh, you're saying like this increase the whole size?
Yeah. but if I just like, yeah, I guess you could like, you can make it wider, or you could just, I was thinking just make the whole thing twice as tall and then rehash everyone. But you can also make it wider.
But just by making it taller, the cycle would still be a problem.
You then have to rehash everybody. So on average, like everything would be half full as it was. But you can also make it twice as wide. And that would also fix the issue, because now you can keep kicking. Or like now you have a space to kick into.
That would have been thought that the problem. It's like now in the system. Like, for example, in the case of quotient filter, we did like keep moving the bits till you are in the free space.
Yeah.
But here you're like constrained.
Yeah, but in the quotient filter, like eventually, like in the limit, like you may have no spaces. I guess if it's 100% full. Even in the quotient filter, you may have to resize sometimes. Here, like, as you said, like if you get a cycle, you may resize like before the whole thing is 100% full, but it is, you can fix it, I guess. And I guess over Bloom, like Bloom cannot be resized, but this you can just resize like either horizontally or vertically. And actually the math behind this is really cool, and I'm not gonna prove it, but it's the thing that, it's called Power of Two Choices. And you can look it up, there's a lot of papers, but basically, do you know about like balls and bins? Yeah, yeah. So like, balls and bins is this probability, it's like a probability game where you model things and you have like n buckets, or you have n bins and you have n balls. And you throw the balls into the bins and you try to make arguments about like how full, I mean, I guess it said it here, like how full is any bin after you've thrown all the balls, and how full is like the maximum bin after you've thrown all the balls. So I guess like you throw n bins into n ball, or you throw n balls into n bins, like what is the expected fullness of every bin? Yes. Well, an expectation is like one. Like on average, any bin has one ball. Makes sense? Because like if you add up all the balls, you divide by the number of bins, they're equal, so on average it's one. But as you say, like they're centralized around a normal curve. And you can prove, yeah, so you want to, people usually, okay, so one main application of this thing is for load balancing. Because like you can imagine that the balls are like jobs and the bins are like servers that are doing the jobs. And you want to do some kind of randomized load balancing without coordination. And so you want to make arguments about this load of the bin, which is how many balls are in any of the bins after you finish. And you want to make arguments also about the maximum load, which is like over all the bins, what is the tallest one in some sense. And you can, and this old theorem from 81 tells us that if the balls are thrown into the bins independently, just uniformly at random, you get a ball, you pick uniformly at random one bin, and you throw it into that bin, the maximum height of any bin at the end is log n over log n. So it's pretty much like log n. But one really amazing theorem that they first proved it in 94, but then I guess the person who made it more famous is he wrote a thesis about it, doing it in different settings. Because this setting is kind of constrained, like first you'll notice that it's static, like you need the number of balls and bins up front. But like suppose that you had a dynamic system where like the balls are just that, like you may like sometimes balls leave the system in true, if you're imagining this as like tasks will leave the system eventually, they finish. So in the thesis, they study like this dynamic, like steady state type of thing, and they also study the parallel version of this. But anyway, the most basic version of this two-choice theorem says for every ball, if you choose two bins and uniformly at random, and you place the ball into the less full one, you can reduce the maximum load to log n. So you can get this exponential improvement by just choosing two rather than one. I thought this was really cool when I first learned it. And also, if you choose more than two, it doesn't really help you. Like, it improves the base of the log, but like this is log base 2. But if you like choose 3, for example, this is like log base 3. So it's really like the huge drop comes from like 1 to 2. Yeah. I'm not going to prove it, but does it make sense how this applies to the previous thing? Yes.
Wondering what that graph log n looks like.
Graph log n?
It's always very.
Yeah, it's almost like it's close to constant. Because like log is already not increasing very fast, and log is like log of that, so it's even less. Yeah, so this is, yeah, so this is like one of these old famous theorems, and it turns out that it's pretty powerful to choose two things rather than one. And there's a survey about it, and there's lots of papers about it. It's called Power of Two Choice. And that's why in cuckoo filters, they choose two things and they keep kicking. Because you want to make some argument about how full each block is. Okay. So cuckoo filters, again, these are lower bounds. For locality, you have to do these random probes, if you check these two boxes. And the size is n, the lower bound is n log 1 over epsilon plus 3n. Is the constant. Okay. So recently there has been this paper from 21 about vector quotient filters, which is how to overcome this time-space trade-off in filter design.
Why? Okay, go back to this. Why
Uh-huh.
should we not have to why is it constant? Doesn't it depend on the n?
I think it depends on the cycle length.
Oh.
Like at most, I guess here, maybe in this example, they fixed the height up to 500.
Oh.
Something, because like the maximum number of kicks you could get is the height of the thing.
Also, so I understand cuckoo filters are similar to like set associative caches, right? Where does the power of two choice come into that? Like what are the two things where like,
The two hash functions,
I see.
and then you choose which, the hash functions tell you like which block to look in, and then you choose the less full one.
I see.
Yeah, and that's how you like load balance the fullness of the blocks.
I see.
Good question. Okay. So, yeah, so this recent paper studies the vector quotient filters, and as an outer layer, they use cuckoo hashing. Basically, they have this 2D array, and the height is n over s. But here they try to make the slots. They try to make the number of slots bigger. Like previously, if you remember, the slots were like 4, but here they try to make the slots 64. So they try to make it wider. But then there's some issues if you just make the thing wider, because then you have to check a lot of slots in your block. So to resolve this issue, like you can imagine, an initial design is like this is just an array, like it is in a regular cuckoo filter. But as a secondary design, they add a small quotient filter in each of these blocks, where each of the blocks is a quotient filter with false positive rate epsilon over 2 and capacity s, where s is like 64. And then to insert the item, they compute, the top level is the same as cuckoo hashing. You compute these two hashes, you insert f of x into the emptier one, and they get rid of this kicking. And it is not, so you might ask like, well, what if it's full? What if both are full? Like, how can you avoid this kicking? And in the paper, they say, they allow this failure that if the both blocks are full by power of two choices, then the insertion fails. But they have this old theorem that was proved in 06, that if you have m balls into n bins using power of two choices with high probability, the maximum load on any bin is m over n plus log log, or natural log. And so to avoid, you basically like, then you use this to determine the size. And so if you have n items, then you can allocate n over ln blocks, and each has this capacity. And then using this theorem, that'll tell you that you have enough space. You just need to allocate enough space so that you never hit, you can accommodate like this maximum load by probability. And then all insertions will succeed with high probability. Okay. So that's how they got rid of the kicking with some space. And yeah, and those two hash functions now can be independent for insert only, and in the proof, or in the paper, they prove that you still need them to be, or this doesn't work straightforwardly for deletes, I think, but for inserts, it just works. Yeah, and then they also, there's this older, also from Bucking, I think it's like in 90, he proved that the variance in the block occupancy is low order term as well.
So by using that theorem, to free out thinking, we have to know the total insertions in what.
Yes. Yeah. Mhm. Good point. But you can resize this like follow horizontal. I think not really horizontal. I think you can only resize up. Right? Yeah. You do have to know it up front. Oh, and because you don't have to do the kicking anymore, the concurrency is easier because now you just insert into the blocks and you don't have to have this like chain of dependency. And inside the blocks, they have this small, like I said, they have this small quotient filter. Every block has B logical buckets, and the fingerprints are just the fingerprints like they were in the initial quotient filter. And they maintain they tell you okay, so the buckets are like the sets in the initial quotient filter. And this metadata tells you how long the runs are in unary. So like, for example, here, since there's two purple things, there's two zeros, and then one denotes the end of the run. And then blue, there's just one of them, so you have 0, and then the end of the run. And there's 2 yellow, so there's 2. Then the end of the run, and there's nothing in green, so there's just no zeros. And then if you want to add, here they add f of x, then you add 1 0 into this bucket, and then everything else gets shifted down 1. And then you can implement these with vector instructions. And they can prove that the space efficiency is maximized when B, which is the number of buckets, is S, which is the width of the entire thing, divided by natural log of 2. And they implement them with these vector instructions. And you can show that in a vector model where the vectors are sufficiently large in size, you can do these shifting operations in constant time. So this vector quotient filter achieves the lower bound in space, CPU cost, and locality. And then they had some data. This is throughput, this is load factor. And I guess the most important thing that they cared about was the large load vectors. And yeah, so this star is vector quotient filter. I see a shortcut, some shortcut like optimizing for low load vectors. It's like you can see that the one with the shortcut is the same in large load vectors, but better in small load vectors. And it is better than all the other ones in the high load vectors. And then these are lookups. And we kind of have, so the Kuka filter is the best for lookups, but again, in second place, you have these two variants of vector quotient filter. And the reason that the Kuka filter is best, I guess it's because the width of the Kuka filter is much smaller. Like the width of the Kuka filter is like 4, whereas the width of this thing is 64. And then they evaluated it on only 4 threads, I guess, but the scale was pretty good. Okay. So to wrap up this part about quotient filters have been used in several applications from computational biology and databases and systems, and in many other areas like graph representations for streams, for key value stores, and so on. Questions? So I will use the rest of the time to talk about filters on GPUs. You probably don't need this motivation, but these days there are supercomputers, and supercomputers heavily use GPUs for acceleration. And one major application that people are interested in running on supercomputers is called metagenomics. And these are some examples, like soil, water, and humans. Metagenomics is the study of microbes that inhabit the environment and their interactions with the environment. And one major problem that people want to solve in metagenomics is called assembly. And the way it works is that you have some sequencers, which are like, I guess this is like on the biology side, like they generate fragments of strings, and those strings are short strings, and those are called reads. And you basically want to use the reads to rebuild longer DNA strands. And that application is really compute and memory intensive. And it's challenging because you don't know what the end result is supposed to look like. And it is like a lot of string alignment, basically. And one tool that people have used to do metagenomic assembly is called MetaHitmer. And these are these many different phases of MetaHitmer. You get all these input reads, which are like strings, and they do these stages on the GPU. They do k-mer analysis, which is doing this analysis on like k-length strings. And based on these k-length strings, they build some graph and they generate some strings from there. And then back on the GPU, they do alignment of the strings and they do assembly of the strings. And then finally, they output like one longer DNA strand. And recently, they used MetaHitmer to do this largest assembly ever on almost 10,000 nodes on Frontier, which is a large supercomputer, and using 37,000 GPUs on this 71.6 terabyte data set. So they're able to do this on huge data sets. And this is the breakdown of the running time. And on GPU, from CPU, they are over 600 seconds. And on GPU, it's around 200 seconds. So you can accelerate the local assembly part, the alignment part, and this k-mer analysis part on GPU. Yes, and then they have a bigger data set that has not yet been assembled. And for GPUs, the main issue is memory, because GPUs have limited memory. And there's this peak memory usage in k-mer analysis, which is when you want to analyze these short strings. And they have this trade-off in GPU k-mer analysis between speed and memory. For speed, or this is like in general for GPUs, you have this trade-off between CPU that you can compute faster, but you have lower device memory. And so you want to optimize for memory size. And one way to overcome this issue is by using filters, because filters are compact. And so you can overcome larger data access by using filters. And for k-mer analysis in this application, they require filters with these several features. You want the performance to be good, or the space usage to be good. You have to support deletions and you have to support values. And there's this issue that existing GPU filters had some of the operations, but not all of them. So these are the initial ones, like Bloom filter and block Bloom filter, which is like a cache optimized version of Bloom filter. Those support inserts and queries, but as we said, they don't have deletions, counting, or key values. And there are these more advanced filters, RSQF and SQF, and those support everything besides counting, everything TM, where it can be theoretically supported, but not yet implemented, especially the key value association, but also the deletions in one of these variants. And in terms of performance, only the block filter was like fast. The other ones are relatively slow on GPU. So the goal is to build this GPU filter that can achieve high performance and supports different features like counting and values. And I will briefly overview this paper that introduces these two new filters. One is called TCF and one is called GQF, built on quotient filters that support all of the features. GQF supports everything and TCF supports everything but counting, and they show some performance cost of the counting. So the main results are these two GPU filter designs. The first one is called two-choice filter, based on the power of two choices. The second one is GPU quotient filter based on quotient filters. And they are up to 4.4x faster than previous GPU filters. And they support multi-threaded point insertions and bulk insertions, and can reduce the peak memory usage in downstream applications. So in terms of design, I'll talk about So in terms of the design, there are several challenges to doing filters on GPUs. That are challenges, I guess, for everything that you ever want to implement on GPUs. First one is thread divergence, which is that you have these units called warps on the GPU, and warps are like 32 threads. And warps, if your threads on the warp want to do different things, they diverge and they slow down because you get warp divergence, which is like you cannot explore different paths in parallel on the GPU on one warp. You have to like follow one path and then sequentially follow the next path. So it's not incorrect, it's just not good for performance. Another issue is memory coherence. This is the same issue. This is like just locality, which is that if threads read different cache lines, even if threads in the same warp read different cache lines, then it is slower than if they all read the same cache line or close cache lines. Another one is limited memory on GPUs. Like the biggest GPU is something like 80 gigabytes, whereas these days you can get RAM that's like 1 terabyte or even more, and GPU memory can't fall back to disk, whereas you can in CPU memory. So you have to fit the entire thing in this small memory. And finally, you have this massive parallelism that you have to design for.
Nowadays, we have also memory to CPU memory.
Yes, yes, it would be slow. Ideally, you want to fit the whole thing on GPU. But I guess, yeah, I guess in terms of correctness, you can offload it to CPU memory. It's true. So there are these design goals for GPU filters. First one is stability, which is if you insert elements, you don't want to move them too far from where they were supposed to go. Another one is low associativity, which means that you don't want location, or you don't want like many locations that an element can go. Ideally, elements go to a small number of locations. Ideally one, but maybe at most a few. And finally, is space efficiency, because the GPU has limited memory, so you can reduce space by avoiding like explicit pointers or over provisioning your data structure. And so there, however, like we have these goals for the GPU filters, but they are challenging in terms of the GPU architecture. So one of the goals was low associativity, but that causes challenges because, well, I guess like it's not challenges necessarily, it just maps onto the GPU design. The reason that you want low associativity is that it can decrease your thread divergence and improve your memory coherence. Because if you only have to access a few locations, that is better than accessing like many random locations. In terms of stability, you don't want to move very far, and that is because shifting is sequential. And so you want to take advantage of the parallelism, and you want to take, and space efficiency because there's GPU limited memory. So the first filter that they introduced in this paper is called this two-choice filter. And it is similar to the vector quotient filter that we just saw. But the vector quotient filter doesn't immediately work on the GPU for several reasons. Yeah, so just to recap, vector quotient filter, they increased the width basically from regular cuckoo up to something like 48, maybe 64. And it can support bigger load factors, but one issue is that it's slow on GPUs because this number of slots is more than the threads on one warp. So you need to use at least, like if you want to use like one thread per slot, for example, then you need to use at least 2 warps, but maybe you're wasting some of the space on one warp because it doesn't exactly line up. And another one is that it's not stable, that each bucket is a filter. So the things may move within the bucket. And you might ask like, why can't you just decrease the width to equal the warp size? And that is true, you can, and that can improve your throughput because now the bucket lines up with the warp size, but it is not good for space efficiency. Can we efficiently use warps with bucket sizes less than 32? Because like we may have some remainder. If our bucket is, for example, size 48, then we don't want to waste half the warp. And in this paper, they use something called cooperative groups, which are recently introduced by NVIDIA. And cooperative groups are this API that NVIDIA exposes that lets you split warps into smaller teams. And this is not like partitioning the warps on the hardware differently. This is just like a software level partitioning. And they trade computation for memory efficiency because they are, of course, less efficient than using the warp just directly, but they can now use the buckets as originally intended, like the bucket sizes. Yeah. And so I guess they did this testing. This is the cooperative group size. It's just a full warp, I think. X is throughput, up is good. Insertion and queries, and then they experiment with the bucket size, like up to 32. And you can see that the best one is here. So the bucket size is 16, the warp size, or the cooperative group size is like 80. And then for queries, the best one is even smaller. And yeah, so the way it works is that you need to do atomics because there are not such strong memory coherence guarantees in GPUs. Like if you remember, like on CPUs, we talked about cache coherence and like invalidating cache lines and stuff. In CUDA, it doesn't work like that. There's no guarantee that the other threads will see the changes unless you do memory fences, unless you do thread fences or atomics. So this is saying in the bucket, every element gets one thread, and you try to use like a CAS to determine to try to insert the element. And all the insertions are used atomically, and all the queries are done lazily. Yeah, and they use this other thing that I don't know if I want to talk about it too much, but there's this recent technique called front yard backyard hashing, which means like you actually use two hash tables and the second one is much smaller. And that allows you to fall back, like if the first table was full in some bucket was too full, but the entire table was not too full, you use this like secondary storage. Yeah, so these are the results. The sizes, the false positive percentages, and you can see that the blue filter is 0.15% false positives, and TQF, or the new one's TCF and TQF. This one is higher, slightly higher, and this one is lower. This is about 2%. And then the bits per item for blue filter is about 10, for TCF is about 16, and TQF is about 10. And yeah, these are the performance numbers. Y-axis is throughput, x-axis is filter size. Probably 2 to the thing. Point inserts and point queries. And yeah, the performance is best for block bloom, both in insert and filtering, but the false positive percentage is high. It's like 0.71 compared to 0.15, and the bits per item is lower, but the false positive rate is much higher. And yeah, these new GPU optimized filters are second. Yeah, and this is some data about downstream applications. So they show that using filter can be much smaller than storing the full data in some hash table. And they can reduce the speak memory usage because you use the filter to avoid storing some of the things in the hash table. So to recap this part about GPUs, this two-choice filter overcomes the feature performance trade-offs of previous GPU filters, where previously, I guess none of them in the table achieves performance except for the block bloom, but block bloom does not have counting or deletes. And it's a simple design, it's just based on power of two choice with straightforward front yard backyard. And using the GPU can vastly reduce the memory use in downstream applications. And that is my last slide. So yeah, I think that's all I had for today. Thank you.